everybody. I'm Philip. I'm a researcher at the Czech Technical University. And I'm not a data scientist or statistician or anything like that. I'm a computer scientist. I do programming languages and software engineering. So it's going to be a slightly different talk in which I will share kind of like a software engineering aspect of developing an R package and kind of a little small tool that we developed and which is quite fun to use. So let me get started. All right, so first to get to know each other a little bit, who is developing R packages in the audience? All right, almost everyone, that's pretty cool. So who's writing tests? Wow, that's about half, that's pretty good as well. So how many tests do you have? What is your code coverage? Does anyone has more than 19%? That's a little bit less, but still very good. So if you have more than 19%, then you have kind of above the sort of a threshold. So I made a little bit of a study. I took 1,500 packages out of CRAN, and I measured what is the code coverage of the tests if you run them. And it turned out to be about 19%. Right? So not much, but there is something. You know, I use the Cover R project, which is really a nice R package which can easily measure the code coverage. All right. So then it goes, who likes to write unit tests? That's surprisingly a lot, actually. I don't, to be honest. It's not the most enjoyable part of coding, but it's really good to have them. This is just a little bit of a slide. So here we have three kind of popular frameworks. Most of the R packages using the testthat, which is somewhat expected, and there are some for RUnit or testit. But still, like, you know, if you look at these numbers, there are not that many packages which are actually using a proper unit testing. You know, there are tests in R, right? Ah, absolutely. Go ahead. I just ran it yesterday, looking for, you know, in the dependencies suggest and stuff like that. It's possible I made a mistake, but yeah. I can show you the code how I generated yesterday. And you know, so there's like a kind of a lot of tests in R, but they are not really a unit test, right? The standard kind of a R test is just that you have a file, you write some code, and when you install the package or when the package is being checked at CRAN, you know, that file is going to be run, and maybe it's going to be checked if you have this kind of a .save file, whether it matches or not, right? But it's not really a unit test or the kind of the idea behind the unit testing. So, well, the idea, what we had was like, so if it's kind of a time-consuming and difficult to write and maintain like a good test suite, would it be somehow possible to generate them, right? And there are many different kind of techniques that we can generate tests, but many of them are not very suitable for the R language because the R language is a little bit way too dynamic for static analysis and other tools which work well for Java and C++. But there might be something that we can do. So let's say that you have this kind of a package function, you know, it's not a very exciting one. And most likely, before you will have even the code, you have something which is using that function, right? And it can be either somewhere in your code, which is being triggered by an example or by a vignette, or it can be somewhere in your clients. You know, many packages have reverse dependencies. There's actually quite a lot of that. So if you look, you know, this is the amount of runnable code of the R packages. And that's amazing, you know, so like there's on average at least 100 lines per package that you can kind of run, right? And that we can leverage to generate the unit tests from. These are the reverse dependencies. So there's 1,700 packages which have at least one reverse dependency, a package that depends on them, right? So again, maybe we can somehow leverage that to generate unit tests. So here's the idea. Maybe a little bit overwhelming, but the idea is that we take a target R package and we instrument all the functions in there in order to record when the function is being called, and we capture what are the arguments and the return value, and a little bit of state as much as we can. Right? And then what we do, we basically gather all the runnable code from the package and from its dependencies. We run all of this by tracing. And now each of these files will contain basically a record that a function has been called, what were the arguments, what was the return value. And then we will try to generate R files in some way. We use the testthat format, but we can use anything what we want, right? and then we will have to rerun all of these tests to see which one passes. And then we can even minimize them, right? We don't want to keep the duplicates. We would like to only keep the ones which somehow increase the code coverage. So that was the idea. Actually, let me try to do this. Can you all read that, or it's too small? It's good? All right. So here's a little bit of an example. So I have my, my little function. I will just plug in a few more things. So I have my filter function here. It's not very exciting, but it hopefully does what it should do. So it filters numbers if they are even or odd. So that seems to work. So now if I want to trace this kind of a function, and that's really just to show you how the core of our package works, is that I load the library in. Now I decorate my function, and let's see what changed. Now if I look at the body of the function, it's much bigger, you know. Before it used to be just this little code, and now I added a lot more things there. And what I added there was basically, the first line is just to capture the random seed, so I know I can reproduce if there was something happening with the random number generator. And then this is just kind of capturing what is being called, you know, pausing the tracing, and getting all the necessary information. So now, when I call again the same thing, you know, I have the same results, and now I can get the traces back. So if I call the copy traces, and I show you how it looks like, then this is what has been recorded, right? So I have a list of one, that means I have one trace, and each trace is a list of bunch of things. So I have the function name, I have package name, well, I just defined it here, so it's null. Then I have the arguments. So now I know that the access was a symbol to nums. P, the predicate is odd, and then I have all the globals. So it captures the entire scope. So it captures what the definition of is odd is, and what the nums is in its global definition. It captures the state of the seed, and it captures the return value. Okay. So I'll just use this little variable to make my life easier. Let's skip off that thing. That's not that important. I will show you how to generate the tests from this. So now I can just turn this into a test. Let's see how that looks like. So that should be familiar for the people who use the testthat. So we bring the library, we set the seed, and then this is basically a test for that exact call. So here I have the call that I was issuing before, and here is the result. And here's basically just setting the environment. This is maybe a little bit too complicated, and because I wanted to have a little bit non-trivial example, so the isOdd function has been defined based on the isEven. And because I want to recreate this whole thing in a completely new environment, so it can run in a new R session or anywhere, I have to capture everything. So that's why all of this is there, right? All right. The .seed might seem a little bit weird. What it does is, because the state of the random number generator is like a 600 integers, that would not really help to read the test, right? That would be just a big chunk of things. So the kind of a big values we just store in a binary format, right? So we use the RDS to just put them in here. So if I look at the attributes of this string, I'll see that, you know, there is an externals and it's an environment, and that environment keeps all the big kind of matrices or vectors or something like that. No, and the last thing, what I can do is that I can turn that into a file. So this will put a file in the temp. So I see here, you know, that the test file is temp null because it's in no package, filter test1. And if I run it here, I get the result that you again might be familiar if you ever run the testthat. So that's pretty much it. Then I have a bunch of functions which can reset things and stuff like that. Now, so this is like really the core, how the package itself works, and we put some kind of a functions together which help you to play with that. So I've picked up this kind of a package of the internet. This is the rvmin, does a bunch of things that I don't really understand. What was important for me was that if I try to test what is its code coverage, takes a little while, then I see that it's only 3.85%. So I was wondering what we can do with this, right? But what is also important is to know is that this package actually has some runnable code in there, right? I have something in the documentation, and even there is a vignette, which I can leverage, right? And plus it has some dependencies. So maybe I can use all of these to generate something. So here's the way how you can run the whole thing. So this is a gen from package, put the package name that you want to have, all the code that you're interested. You want to generate unit tests. You want to prune unit tests, so only keeping the ones which add something to the coverage. So let's run that. And actually, let me switch now for the presentation because it will take a little bit of time. There is a fair overhead with this. So since the demo worked, I can skip all of these guys and go to the question. So how well actually can something like that work, in languages like R, these automated tests? So what we did, we wrote a paper about it. We looked at a bunch of packages. We tried, there was like some original set. We wanted to have a top 100 most downloaded CRAN packages based on this CRAN's log package. And then we wanted to have just 1,000 random CRAN packages to have like kind of a set. When we run their code, only 1,547 we managed to run on our server. Some of them timeouted, and some of them they had just the kind of runtime errors. But all of these packages which run, there was about 1.7 million lines of code, and these are the sizes of the different examples, vignette, and tests that we run. So it was kind of a big. So in total, there were 5.2 million of the of calls, but only 1.6 million were unique. So we discarded traces, which are basically the same. From that, we managed to generate 1.5 million of tests. 1.3 managed to pass, but only 26,000 made sense to keep because they were actually increasing the code coverage, right? So basically, we were able to reproduce 80% of all the calls that we saw, which was better than we actually hoped for at the beginning. Kind of a side effect was that all those 27,000 something runs 1.9 times faster than the code that they came from. They don't get all the way to the coverage, but it's kind of a neat that it runs quickly. So this is just the breakdown on the errors. Most of the thing which we skipped was if the trace was speaking too big, because then the test would be too big. So we just put a threshold to 0.5 megabyte, and that was it. And there were a bunch of errors in replaying. Most of them were that just there was some kind of a state that we didn't keep, and that's why the test blow up at when we run it. So how well we did go? So this is the original slide that you saw before. This is the 19% on average. And the way how it reads is basically here you have the code coverage, and here you have the percent of, here you have the code coverage, and here you have the percent of packages which is at least that particular code coverage, right? So it's kind of a monotonic. And this was the GENThat did. Right, so we managed, from 19, we managed to do the average to 53%. And it was, you can see like it's kind of in each step, it improved the bunch of packages. We also did the reverse dependencies experiment. We selected 65 packages which had at least 20 dependencies from the set that we had before. We ran that, and in some cases it worked. Not in many, and the increase was not that great as we would have hoped to, but it did something. If you don't have any tests, the thing is that the more dependencies you have, you actually have already quite a good code coverage because the package is popular, so there's a kind of a correlation in there. So let me check how they worked. So it ran. You can look at the result. Oops, sorry, it's this key. So this is the result which you get. This is basically the source. This is the output of the test. This is how long run the test, and this is the code coverage that each of the tests contributed. So it's basically in the increasing order. If we want to see, let's see if this works. So now basically we can just concatenate all the tests. So this is basically a file or like a things how I want to run all these files together. And now if I run it again with the code coverage, hopefully that will not blow up. And it actually did, because I'm running a demo. But the good thing is that we keep the stats. So this is basically, there was 334 of the packages, of all the traces that we had. From that, we generated 334 tests. We run 66 of them, so there was a lot of errors by we cannot reproduce. We kept 9 of that, and that gave us the coverage of 72%. And I think a little bit. So there are a bunch of limitations and shortcomings of this approach in general and of the implementation, because we just couldn't spend all that much time. But so the external pointers are not supported. It's a stateless recording. So we only capture the random seed. This non-standard evaluation does not always work that well. So that's where a lot of problems are coming from. The S4, RC, and R6 object systems are only supported now in the binary form. We don't turn that back into code. We don't deparse it. And the documentation is not the greatest, but that's the work in progress. This kind of a shortcomings of the trace-based thing is that sometimes you might end up with the large tests. So the test might not be the most readable thing in the world. But there are a lot of kind of techniques that we can use to minimize that. If there is any kind of non-determinism, like you are, I don't know, reading something off the web or something like that, that's for sure going to fail. And the tests are going to be as good as the code from which we generate. That's the major thing. And there is a tracing overhead. That's a big thing, because R is not the fastest language. We put a lot of, basically every single function we have to modify, so there is some cost. But 75% of the 1,500 packages, they run under 4 minutes. So it's kind of okay, because you don't do it, on the regular basis. So with that, let me conclude. We have a package which basically help you to bootstrap your test suite, if you like, and here are the first link on the GitHub. That's kind of like a sort of tutorial that we set up to how to use it, and that there is a website. It's not on CRAN yet, and it will probably take us a little bit effort to put it there, because we are using some kind of hidden things from the cover R in order to be able to run quickly to the code coverage, and then we will have to kind of figure it around, because otherwise it will be banned from CRAN for now. So yeah. That's it. Thank you very much.
Questions? We have a couple minutes for questions.
Hey, Philip. How are you creating these traces without knowing the exact inputs the function is called with?
No, I actually do know, right? Because we are running the code. Say it again?
All the ones on CRAN, were they automated?
No, what we did, we just install all the packages, right, locally, and then we run all the code which these packages contain while recording. So for each package, we instrumented all the functions inside the package, and then run the code which was there.
Thanks.
Yeah? Yeah?
So thanks for a great talk. I just wanted to ask, where do you see this fitting GenThat in the package development workflow? So do you envisage it being used on a regular basis, or?
Yeah, so where is in which part of the package development workflow the GenThat should fit in? I think it can go kind of in any phase. The moment you have some code that you can actually run in your package, then you can use GenThat to generate some tests. And then I guess at this point, you will probably look at them, look at the ones that you like. You can keep them, delete the other ones, and then if you have, again, you write more functions, you can do the same. Our original motivation for this was slightly different. It was that we have some people who kind of hack on the R interpreter. When they do some kind of a change, they have to rerun a whole bunch of packages, and then sometimes things breaks. And for them, it takes quite a lot of time to figure out what was the cause for a particular error. So the hope was that with this thing you can kind of get, you can turn the coarse-grained sort of tests or examples or vignettes into fine-grained tests, which will help you to kind of debug where the problem was. Right.
Last question.
Go ahead.
We have quite a few very large projects with sometimes thousands of lines of test that code. And for us, it's very important that these tests are well documented and they kind of mean something, right? So I can figure out what I actually broke when I broke something. You have no chance of providing something like this, right?
No.
Maybe, yeah. Okay, I kind of guess that. And so what is now the advantage of having that compared to something like an automatic reverse test? Because I can run that too, right?
Yeah, definitely. This is just
Can I compare that? So is anything, do I get something from this comparison to a reverse test?
well, I guess I don't have much experience with the reverse test, so I don't know what kind of properties do you get.
Okay, I basically run R command check for everything that depends on me.
Right. Yeah, but here at least, like again, that was the same thing what I was saying before, right? The idea is that here you get something which is very fine-grained, right? And you basically generate a test which hopefully will trigger that particular error, and that will help you to trace where the problem was. That's, I think, the major hope. All right. Thank you very much.